let's look at this last section of chapter number 8, membrane processes. Okay, in this process, it involves the water is pumped under pressure. So there is a membrane, and these membrane have pores inside. So the water is pumped under pressure. And this water pumped under pressure is called feed water. So we need to clean this feed water. We want to take all these organics and inorganics. We need to take all these toxic chemicals out of this feed water. So this is a membrane. And of course, this small membrane opening. So we push the feed water into the membrane, of course, into a housing containing semi-impermeable membrane, where some of the water filters through the membrane is called bremate. So whatever comes out of this membrane, which is the clean water, is called bremate. The rest of the water containing the filtered constituents, whatever doesn't go inside the membrane goes like this, we call it retentate. Okay? The pressure required for constant filtration or flux through the membrane is called the transmembrane pressure. Of course, we need a pressure to push the feed water into the membrane or the semi-impermeable membrane. This pressure provides the driving force for filtration to take place. As the pore size, remember the pore size we were talking about? As the pore size of the membrane decreases because of clogging, all this feed water has all these organics will clog these small pores, and as this pore size of the membrane decreases, the transmembrane pressure increases. Okay? Of course, the flux rate is the rate at which the bremate flows through the membrane area and is expressed as liter per meter square per day or gallon per minute per feet square. The bremate is usually stabilized, okay, disinfected, and sent to the distribution system. Classification of the membrane process. Of course, we will select the type of the membrane based on what? Based on what type of water, what is in the water, okay? Type of the organics, the concentration of the organics, and type of the microbes, the sizes, the percentages. All of this will define which membrane system we're going to be used. Let's say there is microfiltration, MF, ultrafiltration, UF, nanofiltration, NF, and last, reverse osmosis, RO. This is an example of a membrane. Of course, this is the membrane here. This is a semi-impermeable membrane. And this is the influent water, the water coming to the system. We call it feed water. Of course, the feed water will be filtered through the membrane. Okay, this is the semi-impermeable membrane, as we said before. Okay, and then all this clean water coming after it is filtered from the membrane, we call it drinking water, bremates. And whatever comes out not cleaned, we call it wastewater, retentate. So the effluent is separated into bremate for drinking water and retentate streams, which currently becomes waste. One big channel to the water treatment industry is to find beneficial use of the retentate. This is a big problem. At the end, where are they going to send it? Because here, there is high concentration of organics, high concentration of inorganics, and high concentration of microbial life. Where are you going to send it? And of course, in this graph, you can see some classification of 4 pressure-driven membrane processes. For example, if you have the membrane filtration, and if you have the reverse osmosis. Let's look at a membrane filtration, a microfiltration membrane. This initial microfiltration will filter what? Will not allow particle, sediments, algae, protozoa, and bacteria. Every water that has any one of these, microfiltration will kick it out of the system, kick it out of the water. Now, small colloidals and viruses will pass by the microfiltration. But wait, there is the ultrafiltration. The ultrafiltration will kick the viruses and kick small colloids from the water system. So this is, you can see it's a gradual treatment. Now next, what will enter? Dissolved organic matter through the ultrafiltration, divalent anions, calcium, magnesium, 2+. Now, nanofiltration will kick these, will not allow divalent ions, no calcium 2+, and no magnesium 2+, and no dissolved organic matter. Now, what will enter through the nanofiltration? Ionic species like sodium, chloride. This will be kicked out in the reverse osmosis process. Of course, whatever comes from the reverse osmosis is fresh water, clean. Although we don't want the water for drinking to be that level, because here you're gonna lose all these electrolytes: calcium, magnesium, potassium, sodium, bicarbonate. We don't want to lose everything. We don't want to make the water only H2O. We need to have some salt inside. We need to have the electricity going through your body. Okay, so you could play with this 4-process driven membrane process to make sure that your water is really clean, but you have to make it in this gradual selection, because you don't want most of the water go to the reverse osmosis and then being clogged so quick. You need to make it gradual. Okay, and you can see that decreasing pore size, which means increasing pressure, and this is the pore size will be decreasing, and the pressure is also increasing. Type of membrane filter system. Let's say the microfiltration, MF. The pore size of this membrane is 0.1 in nominal diameter. Remove particles, as we mentioned in the last figure, algae, bacteria, protozoa that have sizes larger than the nominal diameter, 0.1 inch. The transmembrane pressure operating ranges are 0.2 to 1 bar, 2 to 15. Okay. Ultrafiltration, UV, has membrane pore sizes as 0.01 micrometer in nominal diameter. Can remove constituents such as small colloids and viruses. Operating pressure is 1 to 5 bar. Nanofiltration has a membrane pore size as small as 0.001 micrometer. You can see the sizes are going down in nominal diameter. Remove dissolved organic matter, some divalent ions such as calcium, magnesium. The transmembrane pressure operating ranges is from 5 to 6.7 bar. You can see the pressure also is increasing. Reverse osmosis, here the filter are considered non-porous and usually only constitutes that are the sizes of water molecules can pass through. Only H2O will pass through. Only H2O. The transmembrane operating pressure here is, look at this, 13.4 to 80 bar. Now there is some typical membrane drinking water treatment plant schematics, and if you compare like microfiltration plant with a reverse osmosis plant, you can see that the source of the water comes, whether this water coming from groundwater, whether it's coming from rivers or coming from lakes. You can see it goes to, first of all, to a pre-filtration and then to a feed pump. And this pumps goes to the membrane arrays. This is the microfiltration is here. Okay, so the water will be filtered and go retenuate here. And you can see that there is a retenuate recycle line optional. Go back and send it again. Okay, and you can see that this is the disposable. And here you'll have the backwash water disinfected, because if you have a membrane and this membrane is blocked now, all the pores are blocked, you need to stop filtration and do backwash. The reason for this backwash is to clean up the pores of this membrane. So there is a backwash water, and of course you have to do some disinfection and treated water to the distribution system. And of course, sometimes they will have air or liquid feed backwash fluid to clean up the membrane. This is microfiltration. Reverse osmosis on the other side, the source water, whether the source water is like lakes, river, groundwater, we add some acid. And we add some anti-scalant. This is one of the tricks of the reverse osmosis. Of course, we do pre-filtration. And then bump it to, because you need high bump here, to the RO. This is the RO. You could, in some plants, they will do some energy recovery, and the concentrate, control valve, concentrate, and disposal. This is the disposable. And then the clean water comes to aeration. You add oxygen. And then once you add acid here, now you add base here to neutralize it, and you add corrosion inhibitor, disinfectant, and then treat it to water distribution system. So this is a very good reverse osmosis, and this is a very good microfiltration schematic diagrams. The operation parameters for some membranes, like if you could see the flux rate for microfiltration and liter per meter square per day, you can see it is for ultrafiltration, nanofiltration, and 12 to 20. So the flux rate being reduced because the pore size here is very small. So there is less amount of water coming in. Well, here there's high amount of flux water. The operating pressure for fresh water and seawater, you can see it here. This is the operating pressure, and you can see how much is the operating pressure here in kilopascal. So there's an increase somehow to reverse osmosis. Energy consumption, of course. There is less energy consumption while we go to reverse osmosis. There is a huge reverse osmosis, especially for fresh water. And of course, more if it was seawater. What are the problems? Of course, if you are having a membrane, you will have some membrane fouling. And how could you control it? I'll show this table that shows fouling by particles. Remember, you have membrane and you have pores, and these pores now plugged with particles. Now we call this fouling by particles. Large particles form a cake on the surface of the membrane. While there is a cake on the membrane, there will be nothing going in. So we have to clean up this. So we should do a backwash. We'll remove particles that are larger than the membrane pore size. So we do a backwash to clean up all the cake from the surface of the membrane. The second type of fouling is biofouling, which is like a biofilm, some type of biological biofilm, which forms on the membrane surface and may secrete extracellular material, which adds up to the fouling. Attachment is strong, so backwashing will not remove it, because bacteria here is so attached. Okay? Now we need to add chemical disinfectant to break up the bonds. So chemical disinfectant like chlorine are added to the feed water. Now it's the opposite, not here. The feed water, you add chlorine to clean up and kill all these cake on the membrane. The last one, natural organic matter, NOM. The natural organic matter adsorbs to the surface of the membrane. It's believed to be higher molecular weight and colloidal fractions of NOM that are of sufficient size to restrict membrane pores. Adsorb and then restrict. Of course, we have to do careful removal of NOM through coagulation, filtration, and biofiltration. The next process is adsorption. Okay? What are the type of adsorptions available for us? Well, First of all, before we go to this, we need to know what's the definition of adsorption. Is to remove organic and inorganic materials from water and air. For example, there's something called granule activated carbon, powdered activated carbon. These are widely used to remove synthetic organic carbon. And of course, to remove also odor compounds from drinking water supplies. There is a law in the US called the Safe Drinking Water Act. The Environmental Protection Agency has designated that the granule activated carbon is the best available technology to remove many organics, many inorganics from water supplies. For example, the granule activated carbon is a good technology to remove synthetic organic chemicals, arsenic, and radiology materials. Also, this granule activated carbon is widely used to treat indoor air. For example, removing formaldehyde, toluene, and radon from air. Of course, what is the definition? Another definition of adsorption? It's the transferred. The molecules are transferred from a fluid stream and concentrated on the solid surface by physical forces. This dissolved molecules in the fluid stream, whether it's gas or aqueous, that is attracted and absorbed to the solid surface is called adsorbate. The solid surface into which the adsorbate is adsorbed is called adsorbent. Okay? So the chemicals in the water is called adsorbate. The filter itself that this organic will be adsorbed to is called adsorbent. Of course, once they are adsorbed, there is a physical attractions which is controlled by van der Waals type forces, which is non-specific binding mechanism. Attractive forces on a molecule level, very small. Or the attractive forces between adsorbate and the adsorbent surfaces. Of course, the synthetic organic carbon are amenable to adsorption are those that are hydrophobic, which is water-faring, they hate water. Those that are hydrophilic, which these are the one loves water, prefer to stay in water. So their affinity to adsorption is very low. So you have to look for these chemicals. Are they hydrophilic or hydrophobic? Okay. The adsorbent type, remember, as we said, there is adsorbent and there is adsorbate. This is the actual activated carbon. Now, adsorbent type, the widely used adsorbent is activated carbon. Activated carbon is the granule activated carbon or the powdered activated carbon form. Another adsorbent is granule ferric hydroxide. Okay, this is used primarily for removing arsenic and selenium. In comparison to granule activated carbon and powdered activated carbon, GFH, the granule ferric hydroxide, has a specific surface area, huge, 250 to 300 meters square per gram, with particle size ranging from 0.3 to 2 millimeters, very huge. These adsorbents are porous and have a large internal surface area for adsorption to occur. The high total specific surface area for the adsorbent provides many sites for adsorption to take place. You can see that there is some example of here in this table of synthetic organic compounds that could be adsorbed, and some of them not technically. There is some favorably adsorbed or unfavorably absorbed to activated carbon. Okay, if you look at atrazine, it's easily adsorbed, while acetone not easily adsorbed. Benzene easily. There is a favor to absorption. Carbon tetrachloride, chloroform, while ethanol, no, doesn't like to be absorbed to activated carbon. So this table could tell you which chemical. Not all the chemicals will be absorbed to activated carbon. Some will and some will not. If you compare between granule activated carbon and powder activated carbon, you can see the following differences. The primary use for granule activated carbon is to remove organic constituents, inorganic constituents such as mercury, fluoride, perchlorate, and arsenic. Specific surface area, look at this, 500 to 2,500 meters square per gram. Particle size, 0.3 to 2.4 millimeter. Of course, the design concentration here, that this should be carried out in a fixed bed mode of operation, either as a gravity feed or under pressure. The three common mode is single adsorber operation, or adsorber operated in parallel, or adsorber operated in series. This is for granule activated carbon. While the powder activated carbon, primarily for removal of seasonal taste, odor, also used for periodic problems with agricultural pollutants such as pesticides and herbicides during spring runoffs. Now, look at this total specific area, 800 to 2,000 meters square per gram, while the particle size, 0.044 to 0.074 versus this. This is different than the granule activated carbon. Here we inject it at the head of the conventional water treatment plant and remove during sedimentation and filtration process. Key design parameters is required: dosage, how much, obtained using jar test. We are finishing from this lecture, and then we'll start chapter 9 in the next few hours.